Hey, so today I want to talk about a phenomena related to how LEDs can be used as a load on these RFID antennas, similarly to like RFID chip that you can talk to with a reader. So I've got a chip here. I've got it on a little antenna. You've seen these tags in the environment, and they can read, and then you can use a computer to communicate with the chip. And the way that that happens is the chip has, on the actual die itself inside, has some rectification circuitry that takes the signal from the reader, which is a wave like this, presents a positive and a negative voltage. So the chip takes this signal, rectifies it so that it can be used, and smooths it out and uses it just like you'd use like a battery, say, to power the chip. But another situation that I've been working on lately, we have a bunch of implants and other use cases where you can use LEDs as the load instead of a chip. Now the difference is that the LED, there's no microcontroller or anything in this LED configuration, so you can't talk to it with a reader. But you can use it to detect when the field is present from a reader. And in our use case, we use that for decoration. For some people, they like to have them kind of like tattoos. They have LED implants. But you can also use them to detect what a good orientation is in a field detector or field tester like this, in order to tell how to couple your implant with a reader when you actually want to read. Because it's under your skin, it's going to be a little difficult to figure out that orientation. So to have some kind of facsimile that you can use, cheap little thing that you have in the field, keep in your wallet or something like that, and it'll let you test out readers with a convenient indicator. But one trick that I've started utilizing recently is putting two LEDs on here. So there's two LEDs here, but LEDs have a polarity. They have a positive and a negative leg. So if you can see from the indicators on these LEDs here, their polarity is opposite. So like they're reversed relative to each other. And that provides several benefits in a circuit like this. One, it allows you to have two LEDs, and that gives you more light output, which is convenient. But you can also, when you reverse the polarity like this, you can get a result where with one LED, when you have a normal signal coming from your reader, it's got a positive and a negative portion. But because LEDs have a polarity, that negative portion gets cut off, and you only get half of the power delivered to the circuit, because it's as if when the negative portion of the wave passes, there's no connection. It just gets cut off. The reader isn't wasting that power. It's just not being delivered to the load. But if you have a two LED configuration like this, and you reverse their polarity, then during the positive portion of the waveform, it's going to go through LED 1, and during the negative portion, when it would be disconnected for that LED, it becomes connected for the other LED that is reversed. So you basically get the full amount of power being delivered by the reader, but it's rectifying it so that the LEDs can both experience it half of the time. And because the frequency that occurs at is 13.56 million times a second, it's way faster than our eyes can register. Our eyes can probably register things that flash 50 times a second, where this is 13.5 million, so we definitely can't even see it. There's also, inside an LED, and part of the reason that it works for this application, it has something called capacitance built in. So basically it can store charge. There's a small amount of capacitance in these LEDs. So for each one of these, say it's like 30 picofarads of capacitance, and they're being added together. So this circuit has maybe 60 picofarads of capacitance. And if I work that in with an antenna, like this is a very similar antenna to what the one built into the card, but it was intended for implants. If I work that in with an antenna that's tuned so that the entire assembly will resonate at 13.56 megahertz, I'm going to pick up a significant enough voltage to light the LEDs. Similar to what happens with an RFID chip, they pick up the energy from the field, rectify it, and they're able to resonate at that frequency and get enough power to power the chip. So the interesting thing about the tuning this very carefully and having those two LEDs is that I can use this field detector for basically telling how... this one's kind of binary. Let me grab another. Well, it's difficult to see with the lighting configuration that I have, but if your coupling is poor, then you get a dimmer response from the LED until you get the perfect coupling. There we go. And it gets brighter. So, unfortunately, unlike incandescent light bulbs, these LEDs don't have like a linear response. The way that the LEDs respond is related to how much current is flowing through the LED. Now you can see, as an example, I've tested from a reader and with implant size antennas, I can get good enough coupling to maybe get positive 4 and negative 4 volts on this waveform, and it's being induced into the antenna. 4 volts isn't great though, because for an LED, the amount of current that flows through it, which relates to how bright it's going to be, is dependent on the voltage that is present over the junction, so over the two pads. And for a white LED like this, for example, the response begins at about 2.5 volts, and then it ramps up rather dramatically up to maybe 3.2 volts. You could probably do 3.5 safely, but if you go beyond 3.5 volts, you're creating unsafe conditions for the LED because the junction inside that produces the light is going to overheat and get like physically damaged by those conditions. But when you use an oscillating signal like this reader and you hook it directly up to an antenna and the LEDs, then you are not giving a constant like 4 volts. So you're not exceeding that 3.5 volts threshold constantly. You're only exceeding it at the peak of every wave. So because of this downtime, it doesn't seem like much because it's oscillating so fast, but because of the fact that, like, say, 40% of the time it's below that threshold, during this period when the LED is flashing on and off, it is allowed to cool, the junction is allowed to cool down. So you can actually let the LEDs in this field tester circuit run hot or run at a higher voltage because they're able to cool down in the periods of time in between the peaks. And that's all dependent on the type of LED it is, the conditions that it's in physically, how much heat dissipation it's made to do. And obviously in the body, that's a little bit less ideal heat dissipation than out in the air like this field detector is. But it still works pretty well for implants because of the thermal mass of the implant encapsulation itself and the body, which is mostly salt water. It actually is able to control the junction temperature of that LED pretty well. So we're able to squeeze out a pretty good amount of brightness, but with variable conditions, where I'm creating a very bright light because I'm overdriving this LED because of the really good coupling factor, or a really dim light because I'm underdriving the LED. But overdriving it, I mean, maybe even to 5 volts, if I get the ideal coupling, is not going to permanently damage the LEDs because of this cooling cycle that it's undergoing. So I just thought that was pretty interesting. And the fact that we're doing the reverse biased LEDs, where the polarities are opposite, that's a pretty cool trick. And it really gets a lot of power output out of the readers. So we're getting field powered lighting. And I hope to do more development in that area in the future, possibly because NFC energy harvesting is somewhat limited, especially in a really rudimentary analog condition like this. I have other NFC energy harvesting chips that are actually like dedicated integrated circuits for that purpose, and they can get more power out of the field. But I'd also like to see like a larger array of LEDs being powered by a higher intensity power source, like potentially key wireless charging, what's used for your cell phone. If we could have key wireless charging implantables, then the amount of power and the amount of LEDs and light output they could have would be dramatically increased. Like definitely tenfold more than the NFC energy harvesting we're seeing right now. So yeah, if you have any questions, put them in the comments, and we'll see what we come out with in the future.